Okay, guys, we are all set. So over to you, Deepika, ma'am. The virtual stage is all yours. You can share your screen.
Sure. Thank you, Manish. Please confirm if you can see my screen.
Yeah, ma'am. It is visible to me. So audience, please confirm in the chat section. Is it visible to you as well? And ma'am is audible as well? Yes, ma'am.
Okay. Thank you, Manish. Good afternoon, everyone. Thank you for joining the session. I am Deepika. I work as a lead data scientist at Johnson & Johnson. So in the past, I have worked with Ernst & Young, Bridge-I2I, and Genpact. And as Manish mentioned, my areas of interest include machine learning, deep learning, NLP, and graph mining. So in my 7 years of experience, I have majorly worked on supply chain projects in the areas of inventory optimization and demand forecasting. So the topic for today's session will be Introduction to Part of Speech Tagging and the Hidden Markov Model. Yeah, so the agenda for today's session is understanding the part of speech tagging. Why is it important? What are the applications of part of speech tagging? What are the different types of POS taggers? And I will be walking you through this hidden Markov model, which is used for POS tagging. There are certain prerequisites to understand the hidden Markov model. So the last 5 to 10 minutes, I will lock it for Q&A session. So let's get started. So what exactly is this part of speech tagging? So part of speech tagging is the process of labeling words in a sentence with their respective parts of speech. So basically, in simple terms, we are classifying words into their grammatical categories. I'm sure all of us would have come across this as part of English grammar during our school days, and this is applicable for any language. If you look at this sentence, I like to read books, what we are trying to do over here is tag each word in this sentence with their corresponding parts of speech. For example, I is a pronoun, like is a verb, to is a preposition, and so on. But why do you think this is important? If you look at this example, there are two people. Person A says, I really enjoyed the play, and person B says, I am in a band and I play the guitar. If you look at the word play, it's a homonymous word, which means they spell the same. They can sound similar, but their meanings can be completely different based on the context. So, as human beings, it is easier for us to understand the context of this word. But for a machine to understand the context of the word, pause tagging becomes crucial. And which is why pause tagging helps algorithms understand the grammatical structure and meaning of a text relevant to the context. If you look at this example, it says, we got a loan from the bank. The word bank here refers to a financial institution, whereas the second sentence, we are sitting on the river bank. Here, bank can mean something else. As human beings, we understand the context of this word, but for a machine to understand the context of this word, pause tagging is essential. And hence, pause tagging may not be the solution to any NLP problem. It can be considered as a prerequisite to simplify a lot of NLP problems, which I will discuss in the next section. So I have highlighted few more examples here, similar to this. Moving on to the next slide. So what are the applications of part of speech tagging? So part of speech tagging finds its application where machines are trying to deal with text data, be it in verbal or written form. For example, speech recognition. I'm sure all of us have come through Siri or Alexa or Google Assistant, where you pick up and say, hey Siri, is bat a mammal? Versus asking Siri, who is the best bat manufacturer in India? So if you look at these two questions, which involves the word bat, Siri has to understand the context of the word bat in this sentence. And for Siri to do the speech recognition, tagging the word becomes crucial, and which is why POS tagging is important in case of speech recognition. Coming to sentiment analysis, where we try to categorize the sentiments as positive or negative or neutral, which finds its application in social media. Basically, if you look at platforms like Twitter or YouTube, where a lot of opinions gets expressed, it is important to categorize the sentiments as positive or negative or neutral. In order to do this, POS tagging would be the first step. For example, if you look at this word happy, it indicates a positive emotion, whereas not happy indicates a negative emotion. For the machine to understand this, we have to do the POS tagging first. Coming to machine translation, where we are trying to translate, let's say we are trying to translate a document from English to any Indian vernacular language, or we are trying to translate from one language to another, POS tagging plays a crucial role here. So let us take this example. They might at any time turn against their masters. So if you look at this sentence, the word against is a particle here. If you combine it with the word turn against, it becomes a verbal phrase indicating distrust. So basically, if you're converting this from one language to another, POS tagging is very important. And similar to handwriting, similar to machine translation, it finds its application in handwriting recognition as well, which is useful in case of keyword detection in a document. Coming to the grammatical analysis part, I'm sure all of us have come across this application called Grammarly, which goes one level beyond doing the spell check. It also tells you the next possible word. I'm sure all of us have come across this situation when you write emails, it tells you the next possible word and you hit on tab and it completes the sentence. So for a machine to do that, POS tagging is very important and it is a prerequisite to arrive at that solution. Coming to gene prediction, I would say gene prediction is an application of hidden Markov model, which I will explain in the later section. So essentially, there are two kinds of POS taggers. One is a rule-based approach, and the other one is a stochastic approach. In case of a rule-based approach, we try to come up with certain set of rules in order to arrive at the POS tag. So there are two stages to this. In the first stage, it uses a dictionary to assign each word with a list of potential POS tags. For example, if you look at this word act, it can appear as a verb or as a noun. So in the first stage, it will assign all possible POS tags for this word act. And in the second stage, we have a certain set of handwritten rules which will help you arrive at a conclusion. So in the second stage, we basically tag if the word act will appear as a noun or as a verb. This is based on certain set of handwritten rules. So if you look at this example, if the preceding word is an article, then the word in question must be a noun. So you basically code this information in form of rules to the machine. Coming to stochastic tagging, the term stochastic tagger can refer to any number of different approaches to solve this POS tagging problem. Any model which incorporates your frequency or probability based approach can be labeled stochastic. Both of the approaches are quite intensive, but they come with their own set of challenges. In case of rule-based tagging, it is quite difficult to identify and assign the rules when you're dealing with huge corpuses. Let's say you're dealing with thousands of documents or you have to translate a book from one language to another. In that case, it is quite difficult to define the set of handwritten rules. In case of stochastic tagging, I would say it is biased more towards the corpus you're dealing with because the probability of a word is again based on the corpus you're dealing with. You might end up with a valid tag for a given word, but it can also yield you wrong tags at times. For example, the word park, based on the context, it could be a noun or a verb. If in your corpus, if if it has appeared as a noun, it will always predict it as a noun than as a verb. So these are certain challenges in terms of these two approaches. So one solution to this would be a hidden Markov model. What exactly is this hidden Markov model? It is a probabilistic model that allows you to predict a sequence of unknown variables from a set of observed variables. So I'll come to this concept of unknown and observed variables later. So prior to this, let us understand some prerequisites here. So the concept of conditional probability, I'm sure all of us have gone through this in our, during our school mathematics times. Conditional probability basically states that an event A will occur. What is the probability that event B will occur given that A has already occurred? So to give you an example, given that you drew a red card, what is the probability that it is a 4? So the probability of 4 occurring given you have already chosen a red card is what conditional probability is all about. And Bayes' rule is an extension of conditional probability. It basically describes the probability of an event based on prior knowledge of conditions that might be related to the event. To give you an example here, what is the probability that India will win a match against Sri Lanka, given that it has already won a match against England? So this is what we are trying to achieve through Bayes' rule, which is again an extension of conditional probability. So these two concepts are used in hidden Markov models, and HMM is also based on this Markov assumption, which basically tells that the probability of a particular state is dependent only on the previous state. So when you type an email which says, please find the, you automatically get suggestion for this word attached, because it is the word attached is suggested because of the previous word the, and the word the is suggested because of the previous word find. So this again is because of the corpus which we have incorporated during the training process. Next is the output independence. The probability of an observed output depends on the state that produced the observation and not on any other states or any other observation. So this is quite tricky to understand right now. I will probably explain you this with an example. Ultimately, through HMM model, what we are trying to achieve is, given a word, what is the POS tag? So this is how a typical HMM model would work. As we all know, it is a probability-based approach. As I mentioned earlier, I will come to this concept of observed and hidden states later. So there are essentially two kinds of probabilities we will be dealing with in a hidden Markov model. One is transition probability and the other one is emission probability. In case of a transition probability, what we are trying to do is, given a sentence and given the POS tag, what is the transition probability from one POS tag to another POS tag? For instance, how likely is it that a noun is followed by an article, which is followed by a verb and then a noun? So this will be quite clear when we move to use case 1. And emission probability basically tells us probability of a word belonging to a particular POS tag. So in this case, probability of act being a noun or probability of act being a verb. So this is emission probability. Ultimately, as I mentioned earlier, what we are trying to do is, given the word, what is the POS tag based on the transition and the emission probability is what we are trying to do through hidden Markov model. So before we go ahead with hidden Markov model, there are a lot of open source corpuses which are available online. We have Pentree Bank from University of Pennsylvania. We have Stanford University's POS tagging corpus. We have Wall Street Journal's own POS tagging corpus. So there are a lot of open source tools which are available to arrive at this matrix. And the way we will be implementing HMM model is through tools like Stacy or Hugging Face, or there are predefined packages in Python which will help us do the job easily. But it is also essential to understand how this works at the backend. So let us try and understand this through an example. So here I have a sentence, I drove to park. So given the sentence, disambiguate the appropriate POS tag for the word park using HMM model. So here, if you look at this sentence, I am quite clear about the POS tags for the word I, drove, and to. In case of this word park, it could mean a place or it could also mean parking a car. It can be a noun or it can be a verb. So how do we arrive at the right POS tag for this word? So there are, as I mentioned earlier, there are two kinds of probabilities which we will be dealing with. One is the emission probability and the other one is the transition probability. So this information, I have taken it from the open source corpuses which are available for free online. So let us look at this emission probability. Emission probability basically tells us the probability of a word belonging to a particular POS tag. So in this case, what is the probability that the word park belongs to a verb? It is 0.68 or 68%. And similarly, if you look at the probability of word park belonging to noun, it is 0.8 or 80%. The emission probability alone cannot decide the POS tag. We also need the transition probability. So in case of transition probability, what we are trying to understand is what is the probability that my current word park belongs to noun given my previous POS tag is a preposition. So usually in certain open source corpuses, the word to is tagged to the POS tag to. And in simple English grammar, it would mean preposition. So as I mentioned, what is the probability of the word park belonging to noun given my previous POS tag is 2? The probability here is 0.83 or 83%. Similarly, what is the probability of the word park belonging to verb given the previous POS tag is 2? Here it is 47%. So these are the probabilities possible probabilities which we have for this word park. And let us look at this example, like how do we arrive at the POS tag? So here I have highlighted the transition and the emission probability numbers, which we saw here. This basically tells me probability of the word park being a noun, given my previous POS tag is 2, it is 83%. And similarly for verb, it is 0.47. This tells me probability of park belonging to noun, it is 80%. And for verb, it is 68%. Now, how do we arrive at a conclusion? Multiply these two probabilities, and the one with higher value will be the final POS tag. So in this case, the appropriate POS tag for the word park using HMM model would be noun. So this is how typically a POS tagging using HMM model would work in case of sentences. But there can be scenarios where we are dealing with sequences. The gene prediction example, which I mentioned earlier, we will be dealing with sequences instead of a sentence or a text. So let us look at that example now. So in case of use case 2, what we are trying to do is I have a set of observed sequence and I have a set of hidden sequence. So given the observed sequence, what is going to be my hidden sequence? So this is what we are trying to achieve. So I will try to explain this with an example. So we have recorded the weather conditions for 3 consecutive days and also its impact on a person's mood. On day 1, the weather was sunny and the person was happy. On day 2, the weather was sunny, but the person was grumpy. On day 3, the weather was rainy, but the person was grumpy. So on day 4, 5, and 6, I have the observed states of the person's mood. I'm supposed to come up with the hidden state. I'm supposed to figure out the weather conditions. So how can we achieve this through hidden Markov model? Let us understand that. So here I have this probability chart, which basically tells me this indicates the start or the day zero. So at day 1, there is 20% chance that it can be sunny. And on day 1, there is 80% chance that it can be rainy. So given my weather is sunny, there is 80% chance that a person can be happy. And given the weather is sunny, there is 20% chance that a person can be grumpy. Similarly, if you look at this node rainy, given the weather is rainy, there is 40% chance that a person can be happy, and there is 60% chance that a person can be grumpy. So if you look at all three nodes, the total probability will always be 1. So in this case, it is 0.8 plus 0.2. In this node, it is 0.8 plus 0.2 again. In this node, it is 0.4 plus 0.6 again, which sums up to 1 at individual node level. So what about the transition probabilities? So if you look at this example, on day 1, it was sunny. On day 2, it was sunny. So the transition from sunny to sunny is 0.8 here. And if you look at day 3, it has moved from sunny to rainy. So from sunny to rainy, my probability is 0.2. So this indicates the transition probability, which says that which indicates transition from one state to another. It is defined by a probability value. Similarly, the transition probability from rainy to sunny is 0.4. And if you look at this node level, in terms of the transition probabilities, the values will sum up to 1. So it is 0.8 plus 0.2 and 0.6 plus 0.2. So this is how we read this probability chart. So now the problem statement I have in hand is identify the hidden sequence when the observed states are happy, grumpy, and happy, which I have mentioned here. So let us try to understand this. So I have certain hidden and observed states. Observed states are the ones which are quite evident, and hidden states are the ones which are causing these observed states. So because the weather is sunny, the person is happy. That is the assumption we have here. So the set of hidden states here are sunny and rainy, and the set of observed states are happy and grumpy. So as I mentioned earlier, in terms of emission probability, there is 80% chance of a person being happy given the climate is sunny, which is indicated here. Similarly, there is 60% chance of a person being grumpy given that the weather is rainy, which is here. Coming to the transition probability, as I explained earlier, the probability that explains transition from or to the hidden states are called transition probabilities. In this case, there is 80% chance for sunny climate to be in successive days. So if day 1 is sunny and if day 2 is sunny, the transition probability would be 80%. So now that we have all this transition and the emission probability observed and the hidden states, how do we arrive at this sequence? So let us understand that. So if you look at day 1, my weather was sunny and the person was happy. So at the start, there is 20% probability for the weather to be sunny. And from sunny to happy, there is 80% probability. So 0.2 into 0.8 becomes my total probability at the end of day 1. So which is highlighted here. In case of day 2, the weather is sunny and the person is grumpy. So from sunny to sunny, the transition probability is 0.8, and from sunny to grumpy, the the emission probability is 0.2. So it is 0.8 into 0.2. Coming to day 3, my weather is rainy and the person is grumpy. So the transition probability from sunny to rainy is 0.2, and from rainy to grumpy is 0.6, which is specified here. So at the end of day 3, this is the probability I have. Given that the data tells me that on day 4, the person is happy, how do I know if the weather was sunny or rainy? Let us look at that. So on day 4, we know that the person was happy, and on day 3, the weather was rainy. So there are two possibilities here. One is sunny and the other one is rainy. So the transition from rainy to sunny is mentioned here, which is 0.4, as you can see here. And the probability of a person being happy given the weather was sunny is 0.8. So 0.4 into 0.8 becomes the probability for the weather to be sunny on day 4. Coming to the rainy part, from rainy to rainy, my transition probability is 0.6, and from rainy to happy, my emission probability is 0.4. So 0.6 into 0.4 becomes my probability for day 4. And to arrive at the final end result, we will be taking the total probability from day 1 until day 4. But if you look at this value, by default, this is higher and the end output is sunny. So coming to day 5, if you look at day 5, we know that on day 4, it was sunny. So the transition from sunny to sunny would be 0.8. And on day 5, the person was grumpy. So the probability here is 0.2. So it is 0.8 into 0.2. And coming to the rainy, since on day 4, it was sunny, if we have to transition from sunny to rainy, my transition probability is 0.2 and my emission probability is 0.6, which is specified here. So based on this value, we know that 0.8 into 0.2 yields a higher value, and the hidden state in this case would be sunny. Coming to day 6, now given that we know day 4 and 5 are sunny, we will move on to day 6. The person was happy. So basically, the transition from sunny to sunny would be 0.8, which is given here, and sunny to happy is also 0.8. In case of sunny to rainy, the transition is 0.2, and the person being happy is 0.4, which is this. So if you compute the overall probability, you can see that the final sequence which we will be arriving at is sunny, sunny, and sunny for the observed state, which is happy, grumpy, and happy. So this is how a typical hidden Markov model would work. And the second use case, which I explained, it finds its application in gene prediction, where we are trying to find the protein sequences or the structural, based on the structural RNA or tRNAs. So this is how a typical hidden Markov model would work in case of identifying the sequences. So there are two different use cases for which you can use this hidden Markov model, and all of this can be done using Python, or there are a lot of open source tools available online to execute this. But it is also essential to understand how exactly it works in the backend. So this is pretty much it about the POS tagging and the hidden Markov model. We can move to the Q&A session.
So before we proceed to answer your question, audience, I would like you to request our attendees to please fill in the poll about the feedback, as it helps us to conduct most of the session. Yes, now you can throw your questions at us. Ma'am, one question is from Aswin. So he is asking, can you explain the use case of HMM?
Yeah. Okay. So here what we are trying to understand is I have a sentence and I'm supposed to assign the appropriate POS tag based on the context. So if you look at this word park, it can be a noun or it can be a verb based on my context. The word park can refer to a location, as I mentioned earlier, or it can also mean parking a car. So how will a mission come up with the appropriate POS tag using HMM model? So this is again based on transition and the emission probability. So if you look at this emission probability, it essentially says the probability of the word park belonging to verb is 68%, and the probability of the word park belonging to noun is 80%. So if you solely look at this table, the word park belonging to noun has higher probability as compared to verb. But we cannot decide the POS tag solely based on emission probability because it is also dependent on the previous state, which we saw here, which is also the assumption of Markov chains. So which is why your transition probability comes into picture. So here what we are trying to do is, given my current word is a noun, what is the probability that it is a noun given my previous word is a preposition? So here, if you look at this probability, it essentially says that there is 83% chance of current word being noun given my previous POS tag is a preposition. Similarly, there is 47% chance of current word being a verb given my previous POS tag is preposition. Is this clear? Before I move ahead with the calculation.
I think, yeah, yes, ma'am. He has confirmed that it's okay. So he has asked again. So what is PP, PPSS and TO?
So these are the naming conventions that you have from the open source corpuses. It basically indicates if it's a verb, VB indicates a verb, to indicates preposition, NN indicates noun, and PPSS indicates pronoun. So this is how it is coded in the open source corpuses available online. So you can go ahead and check this Pentree Bank, which is by University of Pennsylvania. They have a huge corpus, and this is how a machine would tag a word. This is how a human would tag a word, but if a machine has to tag this word I, it would tag it as PPSS, which essentially means pronoun. Is that clear?
Yes, ma'am, I think it makes it clear. So, ma'am, I think we don't have any more questions. Audience, any questions? Yeah, I think we don't have any questions, so we have to wrap up here only. So thanks a lot, Deepika ma'am, on behalf of Analytics Vidya. So I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such session with you in future. I hope, guys, you have filled in the feedback poll. If not, I request you to please fill in the poll about the feedback, as it helps us to conduct more such session. And we will be having another session from 3 p.m. The link is in the chat section. Hurry up and register for that. And see you in the upcoming section. Till then, bye bye and keep learning.
Thank you, everyone. I hope I was able to explain it well. If you have any questions, you can reach out to me on my LinkedIn. Thank you.
Thank you, ma'am.